Hello and welcome again to my channel. Today I'll be breaking down another LeetCode question number 1514, path with maximum probability. So let's read through the question and understand what we need to do. We'll have an undirected weighted graph of n nodes from 0 indexed, right? Represented by an edge list where edges of I equal to a comma b. That means it will be something like this: edges equal to an array of arrays, right? So a comma b and so on. It's a list of arrays, right? And what does a and b represent? So it says it is an undirected graph connecting the nodes a and b with the probability of success traversing the edge of I, right? So that means this represents an undirected edge from a to b. That means if we have two nodes a and b, we can travel from a to b via this edge, right? So we can go from a to b, or we can go from b to a, and this edge has another property which is a success probability, right? So let's say it is 0.3 in this case, right? And this is stored in another array, right? So array of 0 will be 0.3. Why position 0 has 0.3? Because this edge was in index 0. So that's how edges and this probability array correlate, right? So the probability of edge in index 0 is the probability in index 0, right? Then it says we will be given two nodes, start and end. So we need to find the path with the maximum probability of success to go from start to end and return its success probability, right? So that means we will be given two nodes, start and end, and we are to find a path from start to end, and there can be multiple paths from start to end. We need to find the path with the maximum probability and return that maximum probability. And if there is no path from start to end, we need to return 0. So let's understand this further. So this means, say we have three nodes A, B and C, right? So the probability of this is 0.3 and the probability of this is 0.2. Okay, so there is only one path, and the start node is say A and the end node is C. So we need to move from A to C. So there is only one path from A to C, which is like this, right? So how will we calculate the probability for that? We'll just multiply. So that means our answer in this case will be 0.3 times 0.2, and the answer for that is 0.06, right? Now if there would have been a different path, we would have calculated the probability via multiplication operation the same way, and then checked whether this probability is greater or the other one. Say there was another path and the probability for that was 0.1, then in that case we would have returned 0.1. So that is the question that we need to solve. So this is an example test case, the LeetCode question. So as you can see, these are the nodes 0, 1, 2 and the probabilities related to each of the edges, right? So in solving the question, the first thing that we need to figure out is how to keep track of edges, right? How to find our way from one node to another. Like, how do we know that we can travel from this node to that node? So we need to have a data structure to keep track of that, right? And so we'll make a map and let's call it graph. Let's call it graph, right? And the graph will not only hold the nodes that it can traverse to. So for example, say from 0 we can travel to 1 and 2, right? So for the 0th value, it will not only store 1 and 2 but also the probabilities of each of the nodes. Otherwise we'll have a hard time correlating both of them, right? So it should be something like, for the 0 value, it will have an array of, again, arrays, and the first value will be the node value. That means it can travel to 1, comma, and the probability for that edge is 0.5. And another array saying it can travel to 2 with a probability of 0.2. And if we continue like this, for 1 we will get 0 comma 0.5, basically the same thing because we can travel from 0 to 1 and 1 to 0 with the same values, right? Comma, from 1 to 2 with a probability of 0.5. And then for 2 we will have, we can travel to 1 using a probability of 0.5 and to 0 using a probability of 0.2, and that's where the map ends, right? So this is pretty common in graph questions, and this is called an adjacency list that we have made. So this will ensure, this will help us in traversing the graph, right? So using this we can say from 0 we can move to 1 and move to 2. From 1 we can move to 0 again if you want to, or we can move to 2. So that's how it helps us. The next data structure that we need is a state that holds the maximum values for each of the nodes, right? So what I mean by that is, let's say we have an array, right? And the values are 0, 1 and 2 because those are the only nodes, right? So what we can store here is, say the starting node is 0 and the ending node is 2. So we'll say from to travel from 0 to 0, the success probability is 1 because we already start at the 0th position, right? So this is the start and this is the end, right? Now to travel from 0 to 1, there are two ways, right? 0 to 1, there are two ways, either directly 0.5 or via 2, and the probabilities are 0.2 and 0.5, right? If you see, when we move from 0 to 2, the probability is 0.2, and then from 2 to 1, the probability is 0.5, right? So for this path, the total probability is 0.5, and for this path, the probability is 0.2 times 0.5, which is 0.01, right? And in this case, this is higher or greater than this. So the value at first index will be 0.5, and the value for 2 would be, again, we want to travel from 0 to 2, right? We can go directly and we'll have a probability of 0.2, and from 1 to 2, here the probability will be 0.5 and 0.5, right? So which path do we take? The probability here is 0.2 and the probability here is 0.25, right? So we will take this route and we'll store here 0.25. So this array helps us in storing the max values that we have seen so far when we start traveling from 0 or the start node. And why is that important? Let me show you. So let's say the graph was like this: 0, 1, 2 and then 3, right? The probability was 0.5, 0.5, 0.2 and let's say 0.1 here, right? So the start node is 0 and the end node is 3, right? And we have the array 0, 1, 2, 3. Okay, now the previous values will be same. So here it will be, here it was 1.0, 0.5, 0.25, and now we want to find the value for 3, right? Again, to reach 3 we have two paths. One is 0 to 2 to 3, and the second one is 0 to 1 to 2 to 3. Now the common thing is here is, to reach 3 we have to go through 2, right? To reach 3 we have to go through 2. That means whatever the probability was at the point we reached 2, the maximum probability, whatever the maximum probability was at the time we reached 2, if we multiply that with whatever probability we have to use to go to get to 3, which is 0.1, we get our answer, right? And the maximum probability when we reached 2 was, of course, 0.25 because we stored it. We know this because we stored the value. That's why we need this array to keep track of the highest values we have seen so far, right? Because that's what we will use to move forward. We do not want to use this value when we want to reach 3 because we know this is not the highest value to reach 2, right? So we need to store the highest value to reach 2 so we can use it further up down the line to reach another node. Now let's imagine another scenario where the graph is something like this: 0 to 1, 2 here, 3 is here, and 3 is now connected with 1 this time, right? So we have 0 0.5, 0 0.2, 0 0.5, let's say 0 0.1 and 0 0.1 again, right? So if you think about it carefully, we have two ways of reaching 3, right? Either via this side or from this side. Now since we had the previous values, let's use them. 1.0, then came 0 0.5, then came 0. What was it, 25, and then this is the third place that we need to fill, and that will be our answer, right? So 0, 1, 2. Okay, so now when we have another way of getting to 3, do we still go via 2? Do we still go from 2 to 3? Because the maximum we can reach 2 is 0.25 and the maximum we can reach 1 is 0.5. So do we process 3 from 2 or from 1? Of course from 1, right? But to determine this, we need to traverse the entire array to see which is the highest value. So instead of doing this, we will maintain another data structure called Max Heap. This will always have the highest value upfront. We'll use just a function called pop and we'll get the highest value, which in this case was 0.5, right? So we can directly use 0.5 without even using or having to find out 0.5 by traversing the array. That's where Max Heap will help us. So we need to maintain another data structure called Max Heap, right? So let's check out the code and this will become much clearer. So this is the code of the solution, right? So we have this custom type of node which will have val and probability, right? So moving into a node, we should have access to its value and the probability, right? So we store that here. This is the type max heap and these are the functions that we need to implement to use the max heap from this package, right? So yeah, so this was our first data structure that we saw, which was the graph, right? We have an edges array of array. We traverse over the array of edges, right? We have the value edge and the index of the edge. Why we need both? Because this index is correlated to this probability array, right? So we get u and v. Basically u is the initial node and v is the second node. However, it does not matter here because it is not a directed graph, it is a undirected graph. So we also find the probability using the index, right? And we store the probability for both the nodes, right? So graph of u will append another array of v and probability, and in the graph of v we append uh, u with the probability, right? So it's something like, so we have an u in the array of u we have multiple arrays. This time we are adding another array having v and the probability p, right? And similarly v also has multiple arrays, and we are appending another array having u and the probability. Next, we initialize the max heap using this function, right? And we push initially the start node and 1.0, right? As I said, we always start, we will be given a start node, and the probability for that node will be 1.0, right? Next, we initialize the distance array that will keep track of the maximum values we have. And in the initial, in the beginning, it will only have the start node, and that value will be 1.0, right? Then we'll have a loop that will continue until there are items in our max heap. So heap dot length should be greater than 0, right? Next, we pop off the current node, or basically the maximum value node that we have, right? Because pop always gives us the maximum value node, because this is a maximum heap, right? You can see in the pop function we always get the last item. Okay, n is the length of the old array, and n minus 1 will be the last item, and we return that item. So that's the maximum value of node that we have, or maximum probability of a node that we have currently, right? Then we check if current.val equal to end underscore node. So in the val property of nodes, this represents the node number, right? Either 0 or 1 or 2, right? So we check if this value is equal to the value of the end node, right? Because if we have reached the end node, we can positively return its probability, because that will be the maximum that we have, right? Because as we move in the graph, as we traverse the graph, we always store the maximum value, we never store the smaller value, right? If you remember, so here if you remember, we had two values, right? Either, yeah, we had two values, 0.2 or 0.25, and we stored 0.25. So each traversal, like each move we make from one node to another, we are always storing the max value. So when we reach the last node or the end node, that the target node, we can be very positive that we have already stored the maximum value of reaching that target node. So we don't need to process any further, and that will be our answer. So that's why this clause exists. If the current node that we just popped off, the value of that node is equal to the end node, then just return the current probability, because we know for sure that probability will be the highest that we have found till now, right? Then if current probability is lesser than the value we store in the distance array, then we continue, we do not process that node. Why? Say we are traveling from 0, right? And we are now to travel to 1. Traveling to 1 has two methods, like we can either go from 0.5 like in this way, or like this, right? So in one case we'll have a probability of 0.5, and in the other we'll have a probability of 0.1, because 0.5 times 0.2 is 0.1, right? So say we have stored this in the distance array, right? So distance is something like this, or 0 or 1. We have already stored 0.5 here, right? Now we have already traversed this route and we have stored 0.5. Now we are storing 0. Now we have moved along the second route, and we have found 0.1. But there is already 0.5 stored in the distance array, which is greater than 0.1. So will we store here, or will we even process this node? Because processing this node further means we are not using the highest value. But our whole process is based on the fact that we always use the highest value to move forward, right? So if we use this value to move forward instead of this value, our whole process, our whole answer will be wrong, right? So that's why we do not even continue when we reach this number, because we already have a higher number stored in the distance array, right? So here, that is the condition that helps us in doing that, saying if we ever encounter a current node whose probability is lesser than what we have already seen in the distance array, do not process that node. Because we already have a higher probability in the distance array, use that, or do not process this node at all, right? We do not want to use this road that we have taken, which has led us to a probability which is lesser than what we have already seen. So we do not want to use that road anymore. Okay. Now, finally, we use the graph values that we have stored for traversing, right? So for every neighbor in the array that we have, we'll have two values, next node and probability, right? We stored that. If you remember, this was this. So we are storing the node value and the probability. So that's what we are accessing here. We're accessing the next node and the probability. And we are checking if distance of current value, which is the highest value for the current node in the distance array, times the probability that we have just fetched, is it greater than the value stored in the distance array for the next node, right? If it is, then we update the distance for the next node, because we have just found a higher probability for the next node, and that is this value, because it is higher than this, right? So we update this value and we push to the heap, because this has opened a new path for us, because previously whatever path we have traversed through, we have stored the distance here, right? But we have just found a higher value than that road, so we need to explore that road. So that's why we are pushing it here, right? And that's how the for loop continues until we reach the end node and we return this value. If we never reach the end node, we have to handle that case as well. We return 0.0, right? Because there might be a case where we do not reach, because there is no edge between the starting node and the end node, so we have to return 0.0, and that was mentioned in the question already, right? So see, if we do not have a path from start to end, we return 0. So that's what we do. So that was the solution for this question. Let's try running this. Of course, it will have no issue because I've already ran this, and that is the solution. So this is the entire code. If you want to have a look at it, right? These are the functions we need to specify so that it implements the Max Heap implementation of this package, right? So we implement this functions. In fact, this is the function that makes it a Max Heap, right? If we do this like this, just reverse the sign, it will be a min heap, minimum heap, and for this it is a max heap, right? This is the pop function. It returns the last value, as we have already discussed. The graph function, initialization of the max heap, initialization of distance with start node, and then we go on a loop popping every last node, basically the maximum node, and then using that probability to calculate the further nodes probability until we reach, of course, the end node. So that is it for this video and this question. It is a variation of the Dijkstra solution. Instead of finding the minimum or the shortest path, here we find the maximum probability. That's the only difference. If you found this helpful, drop a like, and I'll see you in the next one.